channel. This is Mr. Yeager. We're looking this time at light. This is going to be kind of a little bit of an introduction to light, the optics unit. We've already talked about obviously waves in a prior unit, and obviously light is another type of wave, an electromagnetic wave. So we're just going to look at a couple of the properties of light itself. Again, this is very introductory. And then after that, we will look at a couple more specific things in terms of what light does in terms of color, and then with mirrors and lenses as well. So here we go. So as I said, even though this particular PowerPoint looks at properties of light, colors, and reflection, I'm going to do properties of light and reflection during this section, and colors is going to be a separate video. Refraction is going to be a separate video. So properties of light itself. Let me get this thing out of the way here. All right. So first off, you're going to hear this a lot when we do optics. When we do optics, light, we're going to say travels in straight lines. So the idea is, come on thing. Shoot, I do need my pen here. Sorry about that. Light does travel as a wave. So it actually travels as a transverse wave. Okay. So again, light is a transverse electromagnetic wave. All right. But because it travels so fast, which is actually what the next slide says, we basically say that this light travels in a perfectly straight line. All right, which is going to make our life really easy, much easier, not really easy, but much easier when we try to start doing some optics diagrams in terms of how images are created. If we had to do it in terms of waves, they'd be very, very difficult, almost impossible in my opinion. But if we look at simply straight lines, that'll make life a lot easier. So light essentially travels in straight lines. We can't obviously see the light bounce up and down. That would be weird if you're looking at somebody. It's not like their image is bouncing up and down, up and down, up and down as you're staring at them. Okay. As I said, light will travel very, very fast. It travels at 3 times 10 to the 8 meters per second. All right. At that speed, it says, you can basically go around the world in 8 times in 1 second, which is pretty stinking crazy. Okay. So again, that's why we basically say light travels in a straight line. It's going so fast, there's no way you can see the up and down motion of it. Okay. We see what is reflected. All right. So this kind of gets us into already some more of the, well, even though it's already physics, this is getting into what we're more talking about in terms of how do we see with this light. And the idea is we're going to see what gets reflected off the objects. You never actually see that. I mean, this is kind of strange. It's not the incident light. The light obviously shines on the paper, but you don't actually still see the paper just because of that. What you're seeing is that paper reflects some of that light up to you, so you can see that. So we are always seeing a reflection of whatever we're looking at, which is very, very kind of like, you know, strange to kind of think about, that everything that you see is a reflection of what actually is being shown. All right. So, already summarizing some things. Like I said, this is probably going to be a very quick video. Light travels in a straight line. Light travels much faster than sound. And again, we see things because they are reflected light. So we're going to get into it in a little bit on the next video, why we see color. We're seeing colors reflected, and those that are not, we don't see, are the ones that are absorbed. We'll talk about. Okay. What we don't, when we see a shadow, all right, shadows is again when light's being blocked. All right. Again, that goes back to just, you know, you're standing out in the sun, you see your shadow because you're blocking that light behind you, the light that's not getting obviously through you because you're a solid object, an opaque object. It doesn't obviously travel through you. Okay, and again, that's why at noon your shadow is shorter because the sun's right above you, et cetera, et cetera. Okay, so we're bringing back the law of reflection. We mentioned it in waves unit before. So one more time, law of reflection, which is going to be a little bit more useful this time. Angle of incidence equals angle of reflection. That's all related to the normal line. Okay, so again, these two angles are always going to be the same. So if it's 30 degrees in, it's 30 degrees out. Never going to get a more difficult problem than that. So very quick about the law of reflection. What we do run into, though, is we have basically, oh, never mind. So here's another example again, sorry. Incident reflected, all right, angles, Okay, so there it is again. What I was trying to say is what we get into is we're going to describe this reflection a little bit more. We have two types of reflection, one called specular and one called diffuse. All right. As it says, smooth, shiny surfaces show you what's called specular reflection. So this would be mirrors, any object that you can actually see yourself. Water, when it's calm, shows specular reflection. All right. So it only occurs on smooth, shiny surfaces because that law of reflection is very clearly defined. Those angles come back, the reflected ray comes back exactly like it comes in. And what happens, we'll talk about this a little bit later, is you see clear images when all of those light rays come back perfectly parallel with you. Okay? They all basically have to come back and intersect basically together. So if they are able to all come back parallel with each other, we can see that image very, very clearly. This is different from what we call diffuse reflection, where as it says, that's when you're on a rough or dull surface, and what happens is the light gets scattered. So it comes in and it bounces off one way, where technically the law of reflection is still being met, but the surface is no longer smooth, and therefore that angle is a little bit tougher to recognize. And you're never going to have to calculate any of this. It's more just understanding. This would be an example of you see a reflection in the water, then you throw a rock in it, and now you don't see a reflection as clearly because the water waves are all out of shape, okay, just scattering that light a little bit more. So same thing goes with basically any surface that you can't really see a reflection on. Obviously, a lot of surfaces are dull, but you don't see a reflection in the wood because, again, the particles themselves in the wood are not perfectly smooth per se. All right. So there's lots of reflection there. So we have specular and diffuse reflection is one of the couple of new terms. The other one I want to hammer here is what we call polarization. And again, we only need to know basically what it is. And so what we're looking at is, the idea of glare, where you're trying to see something, but again, and you should be able to see it. Like this would be where you're trying to look in a glass window. Again, maybe you're looking through a glass window of a store, but you can't really see clearly through it. We have what's called glare, all right? Basically, glare is the idea that it's basically unconformed light. All right, we're going to talk about how polarization makes all the light come in the same way at you. Glare causes the image to be fuzzy. So if we want to get rid of glare, which certain glasses do, sunglasses obviously have certain frames that help them get rid of glare. They are polarized. So you've heard of polarized sunglasses. What this means is it helps reduce the light to a single direction. All right? It's almost like a fence post. When you think of like a bunch of fence posts together, you're only going to be able to get through those fence posts one particular way. You can't maybe get through horizontally, but you maybe can squeeze through vertically. Light is actually coming in at all different directions, vertically, horizontally, diagonally, every possible direction around the 360-degree circle. So polarization is able to reduce this all to one particular direction. So, I'm just drawing dots there. So what that means is, again, the light approaches at multiple angles. So that's what I have down at the beginning of the drawing here, okay? Light's coming in at multiple angles, all right, just like this. You can see, yes, we said it travels in a straight line, but this does take us back to the idea that it is moving as a wave too, all right? So it's coming in at all these different angles and directions. A polarized filter, essentially, is one that you see basically here that's only going to allow one type of directional light to come through at a time. All right? And so basically, in this particular case, they're saying the vertical is what can fit through this particular frame. I mean, almost in my opinion, it looks like the horizontal should go through, but so what? All right, maybe it is traveling horizontally, we can't see it. But the idea is only one type of light wave is coming through. And obviously, many types of these. So it's not like, it doesn't make the image dimmer at all. This is not the whole idea of why it's reducing the amount of light. This is not the, the idea of those car windows that, I can't think of the name of it right now, where basically it obviously shades it, okay? That's not what we're referring to here. So it helps create a clearer image, and most car mirrors are made this way to help you try to make sure that you see that image clearly, and again, sunglasses are made that way. So again, it's mainly just a term that you need to know of allowing only one type of angled light through. Is all you really need to go with. The last thing I'm covering in this particular section is the electromagnetic spectrum. As I said, light is an electromagnetic transverse wave, so you can see that clearly in this diagram. What we're going to look at here is, again, there's many different forms of light. When I say light, obviously the only thing everybody ever thinks of is they only think of the visible light spectrum, because that's what we see. But gamma rays, X-rays, ultraviolet, infrared, microwaves, and radio waves are other forms of electromagnetic radiation or light, essentially. All right? And I mean, it makes sense because obviously we know certain animals that can detect and see the ultraviolet region. There are animals that can detect and see the infrared region. So, I mean, these are forms of light that we and other animals use to see what's happening. Okay, again, reflected. All right, but they are all forms of light itself. The main thing that we're basically going to be using on this is we should obviously know all the different types. That would be one thing that would be expected, is that you know the different types. But that we know basically what type has a short wavelength, has a high energy, has a low frequency, etc. So we're going to look at all three of those as well. Okay. Excuse me. So, I mean, if you look at this right now, sorry, I just want to see one thing real quick. Yep, we'll come back to that. Okay, so let's just use this diagram. The next one just kind of shows some pictures with it. What we obviously see, I want to show here, is gamma. The way I like to try to have people memorize this is just learn the ends, and then hopefully the middle will fall into place. Gamma is, as you can see, the shortest wavelength, but it's the highest frequency and highest energy. So energy and frequency are together. Wavelength is opposite of those. So gamma is the highest energy, highest frequency, shortest wavelength. Radio waves, on the other end, has the longest wavelength, but has the smallest frequency and therefore the smallest energy as well. So anything in between, basically, most questions you're going to get are going to be list these in increasing to decreasing order, or list these in decreasing to increasing order. So if I said, you know, tell me about the energy of ultraviolet, X-rays, microwaves, and radio, and I want to know the energy from highest to lowest, the answer would be, well, X-rays is closest to gamma. You'll be given this diagram in the question. X-rays, ultraviolet, microwaves, radio waves. I mean, maybe not you won't get the exact diagram, so it won't give you all the arrows and stuff, but it'll give you the types of radiation that you need to list and how you try to order them appropriately. Okay? So you're going to get questions about frequency, energy, and wavelength. Be aware, I can always give you colors as well. All right? Now this is backwards, but you might have learned about Roy G. Biv. Okay? Roy G. Biv, obviously that's Viv G. Yor, okay, right there. But Roy G. Biv is obviously all the colors: red, orange, yellow, green, blue, indigo, violet. All right? Understand that violet is the highest energy, red is the lowest energy of any color. And again, hopefully you can remember that, just because obviously it's ultraviolet, which means higher than violet, and infrared, which infra means below red. All right, so if ultraviolet is a higher energy than infrared, purple is a higher energy than red. Okay, that's another way to look at it. All right, so it's mainly going to be these kind of like ranking problems where it's just highest to lowest, lowest to highest. Right here is just another kind of neat breakdown of the EM spectrum, saying what are the size of the waves themselves. So buildings basically are actually, the radio waves are gigantic, are very, very long. So they're actually the size of buildings. Humans are basically in between radio and microwave, all the way down to basically atomic nuclei are the size of what gamma radiation. And you're talking about the particles inside atomic nuclei. So you're getting very, very small there. Again, we could see protozoans and bacteria and stuff, so technically they'd still be in the visible, is the lowest end of that part. So anyway, again, you can see temperature there. I mean, some of this stuff obviously you're not going to have to know. It just gives you a little bit more understanding of the size of the waves we're talking about here. So that is it. That's all I'm going to end at this point. Thank you.